Hello, class. Pardon me. Hello, class. Today we are going to be going over the accelerated motion part 2, getting the last little set of our variables done. Last little set of our formula done. So just to bring it back from where we were at the start, is that we ended up creating two kinematics formula from before, and we used it using 5 common variables. So the common variables that we have are VI for the initial velocity, VF for the final velocity, the acceleration, the displacement, and the time. And of our two formulas, we got two kinematics formula. One of them was the definition of acceleration. Acceleration is equal to the final velocity subtracted by the initial velocity divided by the quantity of time. And the second formula that we ended up creating was displacement is equal to initial velocity plus final velocity divided by 2 divided by time. Now, looking at these two formulas, each one of them has 4 different variables in them, and there are certain pieces that they share and don't, or certain pieces that they share and certain pieces that they don't. If I looked at my first equation, A, VF, VI, and T, the variable that I just don't care about, the one that has nothing to do with that, is the displacement. So if I'm reading a question and there's no mention of displacement anywhere, I'm not looking for it and it's not mentioned anywhere in the question, it seems like that equation number 1 is the one to go to. However, if I was looking at equation number 2 and I'm looking for the variables that are missing, I have displacement, initial velocity, final velocity, and time. There could be an accelerated motion, but I'm not looking for the acceleration. If I don't know the quantity of the acceleration, that's when I'd use my second equation. So provides us some flexibility. I'd be able to find out what's happening in motion that doesn't tell me what the displacement is, or I could find out what's happening in a motion where it doesn't tell me what the acceleration is. This is good, but we have 5 different variables. So what if we don't have other pieces? For example, the question is, what can we do if we don't want to use the final velocity? We just don't have that piece of information available to us. Pardon me. Well, our first equation we got from the definition of acceleration. And the second one we got through our use of graphs and rates and all those relationships we have from before. And so these are based fundamentally off of what they are, but there aren't any new definitions. So what we're doing then is we're just going to combine the two and see if we can get some new algebra. So what should I do if I want to find an equation that doesn't use VF in it? Well, the answer to this is I want to solve for the final velocity in our first equation, and then we can substitute it into the second equation. And at this time, unfortunately, my running through these derivations, they might outpace you and how quickly you can write. If you're having some trouble with how quickly you can write, please be sure to make a note and pause the video so you can catch up. So everybody take a right. Don't be afraid to put up your hand and be like pause, right, and then you can always keep playing it later. All right. So let's continue. So I want to take my first equation here. A is equal to VF minus VI all divided by T. And I want to solve for VF. So I want to get VF on its own. So looking at it, VF and VI, those are being subtracted, and those are both being divided by time. So if I just multiply by time, and what you do to one side, you do to the other. Oops, sorry about that. There we go. Right, that you can see me doing my little algebra in red there. I should end up getting a result of A times t is equal to Vf minus Vi. And that's almost isolated for Vf. I just have to do the opposite of what's happening. So Vf is being subtracted by Vi. So if I just add Vi, and what you do to one side, you do to the other. So I just added Vi to both sides, you can see here. That will get me a relationship finally of the final velocity should be equal to the initial velocity plus the acceleration times the time. So this isn't a new formula. I just did some algebraic rearranging of our first equation. What I need to do is I need to take this new algebra and I want to substitute it into my second equation. So here is my second equation. D is equal to Vi plus Vf over 2 times t. Now what I'm going to do is instead of writing Vf that we see here, I'm going to write D is equal to Vi plus what Vf is equal to. Vf is Vi plus At. So instead of writing Vf, I wrote Vi plus At. And then that all divided by 2. And that's times t. Now, I now have an equation with no Vf's in it. This is an equation with no Vf's in it. This is really good. I'm going to try to just tidy up now. That's what's going on. So I see this bracket isn't actually doing, the inside brackets aren't really doing much. So I can just bring it together. So Vi plus Vi is 2 Vi's. And so I have 2 Vi's plus At over 2. I'm actually just going to separate that addition. And so it's 2 Vi over 2 plus At over 2. 2 over 2 here, the 2 over 2 will cancel out, and the over 2 here leaves us with just 1/2 of the A times t. And notice, however, this is still all in brackets, and we're multiplying out by t. So what I would do is I would take this t and I would make sure to multiply it in to each term because I have to use my distributive properties. So this is going to be Vi times t, and this is A times t again, then divided by 2. And what this is going to give us is D is equal to Vi times t plus half of A times t squared. And that's the reorganization there. So this is our third kinematics equation. D is equal to VIT plus half AT squared. That's one. If anything, I'm going to try to make this look bigger because it's, yeah, there we go. It's a big deal. So there's our third kinematics equation. And what I have there is just a little bit of the derivation, a little bit of the algebra behind it. Now, if you're wondering, like, oh, Mr. Westgard went through that algebra real fast. I'm not sure if I followed. Am I going to have to do this myself? And the answer is no. Once we've derived something, once we've created the relationship, you never need to go through and derive it again. I want to go through and derive it because I want to show you that I'm not just making this stuff up. This stuff comes from somewhere. And our first two relations came from the fundamental definitions. And these two relations are just by reorganizing algebraically. So this relationship, D is equal to VIT plus half AT squared. It's not coming out of nowhere, and it's a relationship that we have and we know how to use. So let's try to put this into a question. So looking on the next page, I see Jacob is driving a car. He slams on the brakes. He slides 27 meters in 3 seconds. The acceleration is negative 4.2 meters per second squared. What was Jacob's velocity before slowing down? So I always like to start by listing out my VI, VF, A, D, and T. Starting off, his initial velocity, what's the velocity before slowing down? That's VI. That is the thing I don't know. I'm going to give that a couple question marks. Time for VF. Do we know the final velocity? Now, in this case, I understand a number of people might say, like, oh, it's 0 because he stepped on the brakes. But if we think about it, you can step on the brakes without actually coming to a full stop. That's just slowing down. And in this case, did we say anywhere that Jacob has actually come to a stop? And reading the question, no, we don't know for sure if Jacob has stopped yet. That wasn't actually part of the question. So VF is blank. I don't know it right now. I can't guarantee. But what I do know is the acceleration that was given as negative 4.2 meters per second squared there. The displacement was given. He slid 27 meters. And the time, you say that goes for 3 seconds. So if I'm taking a look at what I have here, I know my acceleration, I know my displacement, I know my time. I'm looking for my initial velocity. What formula uses initial velocity, acceleration, displacement, and time? Oh, it's this formula that we just created, t is equal to VIT plus half AT squared. So I'm going to start out with this relationship here. So I'm going to write that down. D is equal to VIT plus half AT squared. And now I can just throw my numbers in. So for displacement, for D, I put in 27 is equal to VI times 3 plus 1/2 times, and in brackets, negative 4.2, don't miss that minus sign, times 3 squared. And then I punch this into my calculator. 27 is still 27. VI times 3 is the same thing as 3 VI. And that half times negative 4.2 times 3 squared is going to be negative 18.9. So do a little algebra. I want to isolate for VI, so I move everything else over. That negative 18.9 when it comes across to the other side becomes positive 18.9. Do that addition there, and 27 plus 18.9 is going to be 45.9. 45.9, and that's equal to 3 VI, so divide both sides by 3, and this gives us our final answer. The initial velocity was 15.3 meters per second. Now, one thing to note here is which direction is this was a positive value. The way that it punches in as a positive value, so it is in the positive direction. You can tell the directions are actually given within the question. Slides 27 meters given as a positive number. The acceleration negative 4.2 given as a negative number. I've already given you the directions of positive or negative in the question itself. You could just follow through with those in this question. Sometimes, however, you have to read and get a little bit more context. So I hope we're feeling good with this first example with our third kinematics equation coming in. Notice that the steps that I'm taking, and I admit I didn't draw anything because I don't have my graphics tablet, so I couldn't do a little you don't want to see me draw with my mouse. It's terrible, worse than usual. So I skipped the drawing phase, unfortunately. But you can see I'm still using the same steps as I did before. As I list out my variables, I connect it to my relationship, to the function. I then solve, I do my algebra, and then I come to my final answer there. This is the same stuff that we started practicing last week, so hopefully you're finding this as familiar. All right. Now that is one good formula, but we're going to create another one. What if I don't have a stopwatch? What if I'm not measuring time? How would I do this? Well, we follow the same patterns. You solve for the time in the first equation, and then you can substitute it into our second equation. So if we remember our first equation, A is equal to VF minus VI all over T. If I'm looking to solve for T, it's in the denominator. You'd never want to leave the thing you're solving for in the denominator. So I'm going to multiply both sides by T. Oops, sorry. Just highlighted everything by accident. Whoops. So yeah, there you go. I'm just multiplying both sides by T to move T into the numerator. So that gets me A times T is equal to VF minus VI. And then I don't want to get t by itself, so if I divide both sides by a, then it'll get me t by itself. There we go. I have t is equal to VF minus VI, and that whole thing is divided by a. Now I'm ready to substitute that into my second equation. So here's my second equation. D is equal to VI plus VF, all divided by 2, multiplied by t. Well, the D is equal to VI plus VF over 2. That part doesn't change. It's just this t. T is going to turn into what t is equal to, which is VF minus VI over A. So here it is. All right, notice D is the same, VI plus VF over 2 is the same, but instead of t, I wrote what t was equal to. Pardon me. And that gets me something that looks not so nice, but this is a fraction, and fractions multiply actually pretty simply. Numerators multiply and denominators multiply. Looking at the denominator is actually pretty trivial. It's easy. It's 2 times 8. So it's 2a on the denominator. That's good. Up at the top, we actually have 2 binomials. You might have covered this, you should have covered this in grade 10. When you multiply binomials, you might remember that you use the thing called FOIL. You multiply your firsts, then the outsides, then the insides, then the lasts. FOIL is just distributive property, but in a nice little thing. So I went ahead and I did my FOIL. Here we go. D is equal to first VI times VF, so it's VI VF. Then my outside's VI times negative VI, so negative VI squared. Then my inside's VF times VF, so VF squared. And then my last VF times negative VI, so negative VI VF. And that's all divided by 2a. And while this might seem like a lot, notice how you have VI VF to start with and negative VI VF to end with? Well, positive VI VF and negative VI VF will just cancel out to nothing. So that's very convenient. So we get rid of that. Hooray. And now I have 2a in the denominator, and something's like, you know what, most of you don't like fractions, in this case, let's get rid of the fractions. So I'm going to multiply by the denominator to get it out of the denominator, but you do to one side, you do the other, so multiply by 2a to both sides. And that gets me, and I'm going to do it up over here now. Everybody, this is the way we're going. 2 times a times d is equal to negative vi squared plus vf squared. Well, this is good. This is much easier to look at, much easier to remember. But sometimes people have a hard time with minus signs. So if I just brought this vi to the other side of the equal sign, it comes over as a plus. So I'm going to reorganize this. I'm going to have vf by itself is equal to vi plus 2ad. And that is our new, that is our next formula. There we go. Make that nice and big. There we go. This is our fourth and our last kinematics formula. Vf is equal to vi squared plus 2ad. So here we go. Again, I used my two relationships that we already know. And I just did a little bit of algebra to try to fit them together, and then I tidied them up, and I created my new relationship. So again, let's see if we can put this into practice. We've got Jeffrey throwing a water balloon downward. Now this one, you know what, I am going to do a little drawing. Here we go. We have our water balloon, and it is being thrown downward from a 65-meter tall building, and gravity is accelerating it downward at 9.8 meters per second squared. Now I'm going to keep things uniform. Usually people like to say that up is positive and downward is negative. That's what people usually do, and since I'm not there, I'm going to stick with the usual. Now, if this is the case, what do I know? I know Jeffrey is throwing the water balloon downward. Downward, okay, that means that we have a negative velocity of 3.2 meters per second as our initial velocity. So that's good to know. And then the final velocity was the velocity that it ends with. That's the velocity as it's hitting the ground, so just before it hits the ground. So that's actually the thing that we are asking for. What is the velocity that it is going to hit the ground with? The acceleration is gravity, so negative 9.8 meters per second squared. There we go. The displacement is 65 meters. Now in this case, if I just left it like that, I have actually made a little mistake. The building is 65 meters tall. The building is 65 meters up. But if we look at this problem, the question is about what is the velocity of the balloon. So what is the moving thing? The balloon is the thing that's moving. Did the balloon go up or did the balloon go down? Now, hopefully you're all like, no, the balloon went down. That's the whole point. The balloon is falling down. That means it has a negative displacement. The balloon is the moving object. We check its displacement. It went down 65 meters. And then the time, looking at that question, there's no mention of time in there. So if there's no mention of time, we have VI, VF, acceleration, and displacement under our radar. It looks like our new relationship, VF squared is equal to VI squared plus 2AD, is the one for us. So I'm going to copy down my formula first. VF squared is equal to VI squared plus 2 times A times D. And then I plug in my numbers. VF squared is equal to negative 3.2 squared, and in this case it actually didn't matter that it's negative because negative 3.2 squared is still a positive number, but plus 2 times negative 9.8 times negative 65. You notice if you got one of these wrong, right, the negative or negative, that's when you're actually going to have a minus sign issue. So everybody, please watch your directions. I'm going to be looking at your questions, and I'm going to be looking for you and your directions. I'm going to be looking for those minus signs and make sure that they're consistent. So watch out for that. Then I grab my calculator, start punching it in VF squared. So the 3.2 squared is 10.24, and then 2 times 9.8 times 65 is 1,274. Add those together, 1,284.24. Take the square root, and getting the square root, we get a final velocity of 35.84 meters per second. Now, one thing is I did not supply the direction. Which direction is this going? Hopefully, we all know that this is going downward, right? Because you threw it down, and then it keeps going down, and that just is what makes sense. So if I put in downward, I'm good. Now, some people are like, but Mr. Westergaard, downward is negative, and I took the square root, and it gave me the positive number. What's going on there? How do I know that that's downward when the math isn't checking out? And you know what? That's a fair question. That's a good question. So I want to draw your attention to a little side note here. A little side note. This isn't actual thing. If I just ask the question, what is the square root of 9? That's a simple question. Hopefully somebody out there has said, oh, I know what the square root of 9. It is 3. And I'm like, good. You're absolutely right. The square root of 9 is 3. Why is the square root of 9 3? Well, it's because 3 times 3 is equal to 9. Follow-up question, though. What is negative 3 times negative 3? Negative 3 times negative 3 is also positive 9. So, thinking about that, the square root of 9 is actually not just 3, it is positive 3 and negative 3. Whenever you take the square root, which is what happens here, because we have to take the square root to get rid of that VF squared, you're actually going to have the positive and the negative answers. And you'll have to check and be like, which one is the correct one? And in this case, the negative, the downward is the correct answer because that's what fits the context of the situation. So little thing to watch out for there, right? Because in our previous question, remember I said I'm watching for your minus signs. I'm checking those. This is a case where the math, just trusting your calculator, doesn't keep your minus signs in place. You actually have to think about those more than your calculator thinks about those. So watch out for that there. Oh, that's our new relationships. Hopefully those two examples were really clear. We'll have plenty more practice with these, plenty of time to go over any questions you might have with this. So let's just summarize and wrap things up. We've got ourselves 4 kinematics equations. The first one, acceleration is equal to final velocity minus initial velocity, all divided by time. The second one, displacement is equal to initial velocity plus final velocity over 2, and then that whole thing gets multiplied by time. The third one that we derived today, displacement is equal to the initial velocity multiplied by the time plus half of the acceleration multiplied by the time squared. And the last one that we made today here is the final velocity is equal to the square of the final velocity is equal to the square of the initial velocity plus 2 multiplied by the acceleration multiplied by the displacement. These 4 equations are really the ones that you need. These are the only ones you need for this unit. This is what we're going to be practicing using these for. If you have a simpler one, for example, if you have d is equal to v times t, which you might have done in grade 10, notice how that is actually the same as d is equal to vit plus half at squared, assuming acceleration is equal to 0. So this d is equal to v times t, this only works when the acceleration is 0. And since this whole unit is about accelerated motion, that's not going to happen very often. This d is equal to v times t, do not rely on it. It's actually a bad formula. If you always rely on d is equal to vit plus half at squared, and then you recognize a is equal to 0 in certain situations, it still gets you the same answer, and it will always take things into account. So I strongly recommend use d is equal to vit plus half at squared. Don't use d is equal to v times t. One last note here, watch your units, make sure that your units are always the same. Things will only work when they're in compatible units. And the most common conversion you have to do is when you have to change kilometers per hour into meters per second. If you are ever turning kilometers per hour into meters per second, the kilometers are off by a factor of 1,000, the hours are off by 3,600, so it ends up just being a matter of multiplying by 3,600 divided by 1,000, or what is 3.6. Or if you, for some reason, have to go from meters per second back into kilometers per hour, this is far less common. You'll just do the opposite, which is going to be a division of 3.6. So that's just a little thing for you to remember there. Nothing, right? If you forget, I'll try to remind you. It's not mandatory, but it is helpful to remember that when you're going through problems. Just make sure your units are the same. I hope that was helpful. I hope that wasn't too fast. I'll make sure to post this up so you can always watch it again if necessary. Otherwise, have yourself a good day. See you tomorrow.